transients of a PN diode. Now, what happens is that PN junction diode, as we talked before, is having an inherent capacitance, a junction capacitance across the interface of P and N regions. And due to this capacitance, you cannot turn the device on and off. You cannot have this device behave as a voltage control switch, which is going to turn the current, the direction of the current instantaneously. Okay, it takes time for the charges in the capacitor to settle. So the same thing goes on over here. So since the PN junction diode can be used as an electrical switch, an important parameter is the transient response. That is its speed characteristics as it is switched from one state to another. Well, what it means is, if you look closely at this figure, now you have the forward, let's say forward bias voltage VF connected as such. So this VF is going to forward bias the PN junction over here, and this is done through a series resistor RF. Okay, and this is the state of the diode for t less than 0. Okay, so before time t equal to 0, you have the diode as forward biased, and due to this forward biasing, there is a current ID which flows through the PN junction. Okay, so what happens? The mechanism of the conduction of current is that as VF is applied, the forward biased junction, the holes they tend to diffuse. Okay, the majority carriers. So this is a positive connected to the P-type region, which is having holes as the majority charge carriers in this region. So they are repelled by this positive terminal, and they start diffusing. Okay, they start diffusing on the other side. So once the hole they diffuse across the junction, they become minority carriers. So these holes are minority carriers in the N-type region. Okay, so these are minority carriers. Similarly, what happens is that the negative terminal now is applied to the negative of the external bias. The N-type region is connected to the negative of the external bias. So the electrons from the N region, they start diffusing into the P-type region, okay, and P-doped region. So we have excess of electrons over here. They are going to be repelled. So we have this charge set up, and this charge is again, for example, these are again these are again minority charge carriers, not minimum minority charge carriers in P-type region. So in P-doped region, we have electrons as the minority carriers. Now, what happens is that due to the forward bias, we have this situation that the majority carriers in one region, from P region, they diffuse into the holes, they diffuse into the across the junction into the N-type region, and the electrons, they diffuse from the N region to P-type region, where they become minority carriers. Okay. Now, this is what happens when you forward bias the diode. So we have the electrons diffusing from N to P region. So now assume, for example, the diode is switched from forward bias on state to reverse bias. Okay, and this happens at t equal to 0. So the the position of the switch is now as such that the negative is now connected to the P-type semiconductor region, and the positive is connected to the N-type region. So figure 1.23 shows a simple circuit that's going to switch the applied voltages from VF to VR, and you're going to reverse bias the diode. The point to mention over here is that the reversal of the current from, let's say, IF, which was the forward bias current, forward bias junction current, okay, when the PN diode is forward biased, is not going to instantly switch to IR because of those minority carriers concentration across, which has been diffused initially by applying VF across the junction. Now they have to take some time to settle down. I mean, these excess carriers, minority carriers, they have to settle down. They have to move back to their respective region. For example, once you change the polarity, well, these holes are going to go back into the P region, and these electrons, they are now going to go back into the N region because of the polarities as such, right? So it's going to take some time. The charges are going to take some time to settle. It's just like a capacitor. I mean, once the capacitor is charged, you cannot discharge the capacitor instantly. It takes time. So there's going to be some time before you reach a steady state reverse saturation current, which is going to be due to the minority charges now, not the majority carriers. So it's not going to be an open circuit instantly. Okay, so I mean, if you want to have a look, what goes on with time is that before time t equal to 0, we have this forward current IF, right? Because this was forward biased by the external supply VF, and the current, you can find this IF in terms of, okay, so you have VF and VD appears across the forward bias junction, so the difference of these potential difference between VF and VD divided by RF gives you the forward bias current. This is the current before the switching action actually happens for t less than 0. But what happens at or after t equal to 0 or t greater than 0, greater than or equal to 0, is that, well, you can find the current that is limited by this resistor R. I mean, as a limiting case, you're going to have a reversal of the current, and that will be minus VR over RR, right? So this reverse current is it's going to, I mean, you're not going to have an open circuit. I mean, this IF is not going to fall to 0. So there will be let's say minus IR current, and there will be some time that is required for the charges to get settled. Okay, so these charges which have moved from the region when they were forward biased from P region, the holes moved to the N type region, and then from N type semiconductor the electron have moved to the P type region in forward biasing. What happens now is that it will take some time for the charges to settle, and we call this time as the storage time. So this time is the storage time. Okay, this time is storage time, and then after that it's going to rise. It's going to rise like this. So approximately when this becomes about 10% of IR, that's the 0.1 IR, we call this the settling time. Okay, so this time is the settling time, and before it finally reaches back to the steady state saturation current in which the diode is open circuit. So you see the diode doesn't become open circuit instantaneously. That's the point. And this total time, the settling time, and the time, so let's say this is TF, fall time, before the current falls 10% of IR. Total time is TS, settling time of the charges, plus the fall time of the current is known as the reverse recovery time. Okay, so if I can write this as TRR, reverse recovery time, is the sum of these two quantities, and it takes time for the diode to switch from forward state to reverse state. It doesn't do that instantaneously because of the junction capacitance, right? I mean, it's just like a capacitor. It takes time for both charging and discharging. The charges have to settle down, and this has to be understood in terms of the transient. So therefore, you cannot use your diodes in high frequency switching applications. For example, you can't do that. High frequency switching applications is not suitable. For example, in digital logic circuits or in computers, in microprocessors, you cannot have diodes switching states as a voltage control switch instantaneously, okay, because of this reason. Now, the minority carrier concentrations, okay, so this is again the theory. So minority carrier concentrations for an applied forward bias voltage and an applied reverse bias voltage are shown in figure 124. So again, you see what happens is over here is that there are some electrons when you apply the forward bias, they're going to diffuse across the junction. Okay, so we have excess minority carrier electrons, because in p-type region the minority carriers, well basically you have in thermal equilibrium conditions you have electron, right? I mean, this is the level, this is the concentration of electrons. Similarly on the other side you have the concentration of holes. So but across the junction, when the electrons they start diffusing into the p-type region, they become minority charge carriers, and this is the excess region. So this is the excess minority carriers. Similarly, you have excess minority holes which have been diffusing from P region to N region. So here we neglect the change in the space charge region width. We don't consider that in understanding the switching transient. It's there. So when a forward bias voltage is applied, the excess minority carrier charge is stored in both P and N regions. Okay, so this is what is going on. We have excess minority carrier electron, excess minority carrier holes. This is the forward bias situation. So the excess charge is the difference between the minority carrier concentration for the forward bias voltage and those for the reverse bias voltage as indicated in the figure. So this charge must be removed as the diode is switched from forward to reverse bias, and then this requires some time. This requires time for these charges to get settled. So once these charges they get settled, it's after that the diode is open circuited or a small reverse saturation current flows, and you can see the diode is now is not conducting, right? So it takes time. It's not going to happen instantaneously because it's going to take some time for these excess minority carriers on either side to get settled. So this charge must be removed when the diode is switched from forward bias to the reverse bias. So as the forward bias voltage is removed, relatively large diffusion currents are created in the reverse bias region. This happens because excess minority carriers electron they flow back across the junction into the N region, and excess minority carriers holes they flow back into the P region. So of course they have to settle down. I mean, once the switch has been moved t equal to 0, you switch it to the reverse bias position. The holes and the electrons which have moved on either side, they have to go back into their respective P-type and N-type regions, and they have to settle down before the diode becomes open circuit. Okay, so the large reverse bias current is initially limited by the external resistance RR, which is shown over here. So this current is also, as you can see, this is IR is VR over RR. So the junction capacitance, they do not allow the junction voltage to change instantaneously. So the reverse current IR is approximately constant. Okay. For 0 plus to Ts, which is the settling, or like we call this as a storage time. So, which is the length of the time required for the minority carrier concentration, that space charge region, that is to reach the thermal equilibrium values. Okay, so they will require some time to go back. So that's the storage time, and after this time, the voltage across the junction begins to change. The fall time Tf, typically defined as the time required for the current to fall 10% of the initial value, as we indicated before. The total turn of time is the sum of the storage time and the fall time. Okay. In some literature, the storage time is also called as the settling time. It's the same thing. Settling time and storage time is referred to the time required for the charges to go back from their respective P regions to N region and N region to P region. So once these excess minority carriers on either side have been settled, that is the time required for the charges to settle, and this is the storage time. Then you have the fall time, so you have to add both of them to have the reverse recovery time, RR, okay, TRR, let's say. And this is the time required for the diode to become open circuit. Okay, it's not going to happen instantaneously. It requires time. So figure 125 shows the characteristics of the entire process that takes place. So this is for a situation for when the switch is connected to the forward. The switching is such that the PN diode is forward biased. Okay, so this is when we have a forward biased diode. The current is limited by IF. Okay, and then the limiting current is IR at T. T is greater than 0 positive, just at the instant when when you have switched the diode to reverse bias connection. Okay, PN junction is reverse biased, and then there is some time requirement for the charges to settle. This is the storage time. This is the time when the charges are being settled, and then you have the fall time, which is approximately 10% of the initial current. So both the settling time and the fall time, they constitute towards the total recovery time of the diode, before finally you have this after the reverse recovery time, you have the small reverse saturation current, as happens in the IV characteristics of a diode. Okay, so it requires some time. So this is the current characteristic versus time during the diode switching. So this switching is happening from forward bias to reverse bias, and usually if the transistor is forward bias and it is switched to reverse bias, the reverse recovery time is usually a little greater than the forward biasing. I mean, if for example, okay, let's call this forward recovery time. I mean, this time is when the diode is a reverse bias and you have to make it forward bias. Okay, I mean, you have to switch it back to on state. So the forward switching time is not as long as reverse recovery time. Um, but again, it's limited. Okay, I mean it's not instantaneous because of the junction capacitance. So in both switching states, on and off or off from off to on, you require some time for the diode to conduct or become open circuit. Okay, so in order to switch diode quickly, diode must have small excess minority carrier lifetime, and we must be able to produce large reverse current pulse. Okay, so therefore, in the design of diode circuit, we must provide the path for the transient reverse bias current pulse. These transients, they impact the switching of transistors. Okay, for example, the switching speed of the transistor in a digital circuit will affect the speed of computers. Okay, it's going to affect the speed of clock and etc. The performance of microprocessor and digital circuits is limited by the switching times. The switching states are limited because of the junction capacitances in this PN semiconductor devices. So turn on transient occurs when the diode is switched again from the other way, from the off state to the forward bias on state, which can be initiated by applying the forward bias current pulse. Now the transient turn on time is the time required to establish the forward bias minority carrier distribution. So it's the other way around. Okay. Before we have the majority carriers diffusing into the other region, which become minority, and then if you have to forward bias it becomes the minority carriers. Okay, so the turn on time is the time required to establish forward bias minority carrier distributions. During this time, the voltage across the junction gradually increases towards its steady state value, although the turn on time for the PN junction diode is not zero, but it's usually less than the transient turn off time. Okay, so that's all. I mean, the idea is because of the settling time of the charge. You can think of it as a settling time of minority charge carriers or the minority carrier lifetime. There is a certain storage time or settling time which is required for the transistor or the diode to switch from one state to another. And because of that, the switching does not happen instantaneously. You must remember this. And this is due to the basic capacitor action. The charges, they don't settle down instantaneously. It requires some time to discharge or charge the capacitor, and the same analogy is discussed in this video for the switching of diodes. Okay, so remember that in a practical diode there is going to be some reverse recovery time as well as forward recovery time whenever the diode is switched from one state to another. Okay, it doesn't happen instantaneously. So that's all.